So we will see some second order effects in the MOSFET. First one is body effect, and second one is channel length modulation. So body effect, the first one results in VTH variation, and channel length modulation results in finite RO, non-zero RO, and the subthreshold conduction that results in the non-zero ID below VTH, VGS below VTH. And also the velocity saturation, so maximum current is limited when you apply very large voltage VGS. Okay, we will see one by one and see what kind of the circuit behavior is expected. Let's take a look at the what is required for the channel inversion. We defined the VTH, that is minimum voltage that enable the make the channel is inverted. The electron is attracted underneath the gate, so that is the minimum voltage to forms the channel inversion. But in this case, we assume that the VB body voltage was 0. But what if you have a lower body voltage, then what will happen? So potential, so we are bringing the surface potential up by increasing VG. So if we start from the lower voltage, lower than 0 voltage, then it will make harder to make the channel inversion here. This kind of thing can be visualized here. So for example, for VB equal to 0, then so increasing VG, let's say if the VG is equal to VTH, then we get the channel inversion like that. So, but if we have a low voltage, then we are having a lower potential on the V substrate. So we have a negative voltage. So we have the more reverse diode voltage drop across the reverse the PN junction, and also that creates the so some of the, let's say if this is negative, then the negative charge will be the positive charge, then electron will pushed in onto the P substrate, so it fill in the hole here. The large of a hole previously was there, so more electron is supplied through this body, so it fill in the hole, so it creates wider depletion region. So it becomes harder to make this channel inverted. So if you wanna make this surface voltage to higher, we have to bring this VG even higher voltage, like there's just some delta. Additional delta voltage is required to make the channel inversion. So this such kind of factor is written shown in here. This is the additional delta voltage that vary the threshold voltage. So that is a function of a square root here. So delta is approximately proportional to VSB. So if you have a larger VSB, then VTH increase. What is VSB? So larger VSB. So the base. So we have a source node and base node. So voltage difference between VSB. So source and the body. You can think of the case where the source follower case, so some of this kind of source follower or current source or resistor is tied to a source, some kind of a structure you can think of. then the finite current flows. So drain and source, we have current flows, then there's always a voltage drop. And also for this current source to be working properly, so we require VD must be certain voltage, V greater than overdrive voltage of this current source. So source node is higher for those two cases, higher than 0. So this results in the higher VTH for device than the each source is tied to ground for this device. Even though the same size of transistor here, W over L, so above those upper two cases showing higher VTH. And also this VTH also vary for depending on the output source node voltage. It becomes the function of the source node voltage. That results in some non-ideality like this. Let's take a look at the actual impact on the circuit behavior. For example, without a body effect, the source follower shown on the left, we have a fixed current. Through this device, we will have a fixed current of I1. So the voltage drop between gate and source, GS, is determined by I1. So I1 will, so this one will be VGS will be VTH plus a certain overdrive voltage there. So VGS, this overdrive voltage doesn't change no matter what the Vin is. So if you sweep the Vin like this, VGS change. Does VGS change? No, because the current doesn't change. The current through this branch is fixed by this current source. So there's always VGS difference between input and an output. So here delta is always VGS, meaning VTH plus V overdrive. But if you consider the body effect, then for higher Vin, the output voltage going up and up, in moving, so that if the body is tied to ground, then we are getting more voltage drop between source and we have a VSB here, that is V out, right? Because the body is tied to ground in this case. In that case, then we have a output voltage will be lower because we have a higher VTH plus delta. So for small voltage, for example, we have a, for small voltage we have a difference of a VTH plus V overdrive. But here higher voltage, higher input voltage, there we will get the difference of a VTH plus V overdrive plus extra delta voltage that is caused by the larger VTH. So it might be more appropriate to write down delta VTH prime. So we have a higher than VTH. So VTH changes, so output doesn't follow input properly. So we have some curvature from the output, so that creates the non-linearity. Results in this results in non-linearity. For source follower, the purpose of the source follower is following the input properly, right? In this case, we have a non-ideality. So the signal is distorted. For example, if the input is sine waveform, we were expecting the output like a level shifted down, like the following the input. I better draw more clearly. For example, input is like this, V in and V out is like this, but because of this VTH variation, we will see what higher voltage will get more drop. So what we get is higher voltage compressed, low voltage follow well, higher voltage compressed, like this, right? V out with the body effect. The signal is definitely distorted when you drive the higher voltage. Okay. Now you can think of the base, now additional terminal. So you can have we have a body. So if you change the body voltage, that modulate the threshold voltage, so that creates the current variation delta I. You can model that such behavior as the backgate. So the body can be considered to be a backgate. We have a gate on the gate terminal. The changing in the gate voltage, that will create the delta I. Also, the body voltage change also creates delta I. The amount of current variation is around 0.3 times less, 0.3 times of the actual gate. So we can similarly model that amount of current variation by the transconductance. So the body backgate transconductance is around the 0.3 of the normal transconductance. So some of the circuit technique utilize this fact to maximize the GM. They sometimes provide the signal onto the backgate. This is something that you can think of. Okay. The behavior of a source follower can be written in mathematics like this equation. So we have a fixed current and VGS is in this case always V in minus V out. So replace VGS with this equation. The relationship here like this. For the fixed current, we get this relationship, right? You can work it out to find out the V out will be what? So I1 over 1 over 2 mu n COX W over L square root so this is minus plus V in, right? This is constant, right? For small signal analysis, you can do that. So for small signal analysis, of what you can get is, let's say, if there is a current there, so this is easier for just, let's take a look at the resistive loaded source follower. In this case, let's say V out, it's RL. So we know that. So let's find the small signal gain out of this. For in this case, the change in V in will create the small signal variation ID. That will be given by the gate and source variation. Small signal variation will be ID over GM, right? So this current will be, our current through RL is the V out over RL. So we can equate to find the V out. So small signal variable. So V out is that, what we can see is that ID is equal to, first equation, ID equal to V out over RL, and V out and input relationship is from starting from Vin using KVL. So Vin minus ID over GM equal to what? Vout. So we plug that in, so ID into the equation 2, 1 and 2. So final Vout, the small signal variable, we are saying small lowercase letter. So Vout equal to what? So probably plus 1 plus GMRL. So Vin over Vout will be like this in this format. So if the RL goes infinity, then the Vout over Vin is equal to 1, right? For for finite RL, we'll get this kind of a gain. So having large GMRL will result in the proper small signal gain of 1. But in this small signal analysis, everything is linearized. So we will see some the linear behavior here shown in here. So operating point at some operating point here at this certain voltage relationship, you can find the GM transconductance, right? So that value is extracted based on the actual gate and source. So GM, you will find the small signal variable GM is 2I over V over dry voltage, right? Or other two additional GM equation there. So we can easily find the GM based on this equation. So to find the GM, it is actual value of the GM. It is important to find what is the actual I1 and what is the actual overdrive voltage for the device M1. Let's take a look at the second order effect. ID versus VDS is shown in here. Then typically in ideal current source we have a flat ID versus VDS. So for example, if we assume that ideal current source ID, voltage drop across the current source, let's say IO and VO, then IO versus VO is like a flat. So no matter what the voltage across the current source, the current is always I0. What if we have a non-ideal characteristic, like if you have a resistor across the I0 current source? What would be relationship between voltage and current through this terminal, right? This is the actual IX, for example. Then with RO go to infinite, we get like this kind of characteristic I0. But in reality, by having non-ideal resistor in parallel, we will get like this kind of characteristic. The slope of this guy is IX. Slope of this guy is 1 over RO, right? So basically having this kind of slope, meaning in small signal analysis, let's say in operating point Q, you get like we have a GM VGS, the voltage controlled current source, right? Plus minus VGS. In parallel, some resistor RO. So this RO is the can be found by the So inverse of the round ID over around VDS, right? From this equation, to model this slope, we added this factor 1 plus lambda VDS. So from this equation, we can find that is what the lambda I 1 over lambda I will give us ID, give us the RO from this simple representation, right? So channel length modulation can be viewed in this actual transistor structure here. In saturation, we have a depletion region near drain here. So if we have a larger VDS than higher VD, we will create more reverse voltage on the diode, so it will make more wider depletion region. So actual channel length, this pinch off point move around, and the amount of current density, and also the slope of this guy actually creates a diffusion current. So if they sharper the slope, you will get a higher current. So it can be sort of effective channel length is modulated. So larger channel length, if you have a higher VDA drain voltage, then the wider depletion region and the narrower channel length, so that means the increase in current. So higher VDS voltage result in slightly larger current. So this is the non-ideal effect. So gate surf voltage difference between gate and surf at the location, in each location voltage surface potential go up from the source to drain. So the difference between gate and surface is kind of going down. At the pinch off point, the voltage between gate and pinch off point is VTH. This is where after this point, channel inversion disappear, right? So this is in the saturation. Now the question is, we want to know the slope of this guy, RO, 1 over RO. That is the slope of that guy. That creates the small signal output resistance. That determines the quality. We have RO in this current source in parallel. That determines quality of the current source. Current source is determined. Determine and quality of current source. Higher RO becomes a more ideal current source, right? So it is important to know how we make this RO larger. So in undergraduate course, we model that this lambda variable to model RO, but it doesn't give us how we increase the RO. There is no idea of how to figure out. We need to know what determines the lambda. So actual RO is actually proportional to L and inversely proportional to IDS. So we have a proportionality factor VE here. So why we have a larger L result in larger RO? Because, for example, so we know the physical behavior when VDS changes, the depletion region going up and down. Let's say if we have a smaller channel length, like a very small device like this, the channel length is very small. Then the depletion region, for the same voltage variation on the drain, depletion region is quite wide. So amount of current on the small length device is greater than the large length device. So it is important to have a large L to get the large RO, but this results in larger device size and larger input capacitance. So larger L results in the slow speed. But in some case where you don't care about the speed, then we can increase the L. And also having larger, smaller current will increase the current source. As you can see slightly here, if you have a larger current flows, the slope getting steeper, meaning RO will become smaller. So there's just some tendency between the IDS and L. So we can find that the lambda variable using the proportionality factor VE, that is, so lambda is equal to 1 over VL. So from the undergraduate course we learned that R0 is ID or lambda ID, 1 over lambda ID, right? So this, if you equate this onto here, the lambda becomes what? 1 over VL, right? This guy. Okay. And also there is some tendency also, if you have a higher VDS, higher voltage, you will get the larger RO. If you get the smaller VDS, you see, if your operating point is getting close to triode region, that means you get the smaller RO, right? So having larger VDS helps RO goes up slightly. Such kind of thing, kind of a modeled in equation. If you do more the mathematics, for example, so RO can be proportional to what? L over IDS, and also times square root of VDS minus V overdrive voltage. There's some relationship. So if from the edge of the operating point, the triode boundary between linear and saturation, if the voltage difference, this delta is higher, then you get larger RO. So this is something that you can use your circuit design. Okay. In square law model, simple model, we just assume that the ID versus VGS curve, once the VGS is greater than VTH, then current flow. So here below the threshold voltage there is 0, but in reality there is a non-zero current flows below threshold. So in this low current density, the weak inversion, so we are having slightly inverted surface, so there still we can have a control over the current, drain current, by the VGS. In that region of threshold region, we are relying on the exponential characteristic, right? Exponential VGS over NVT T, right? Vt equal Kt over Q. So and here we just put it like C here. So there's just some factor there, but still it is an exponential function. So in this region, the GM of this guy is very large. So GM in this region is what? Let's see, 1 over CVT times ID, right? So here C is typically greater than 1. So in this case, the GM is proportional to current through this device. So in this region, as similar to the BJT, the GM is large compared to if you for the same amount of current, you get the best biggest GM in MOSFET, because the VT here only 26 millivolt. So if you compare with the GM in strong inversion is 2ID over V overdrive voltage for like overdrive voltage around VOV around 200 millivolt. If you make this number and compare this and that, it's quite order of magnitude difference. So when you think about the efficiency of the GM, we can look at that, they compare GM over ID. So GM, so this is GM over ID case in the subthreshold region, 1 over C VT in wait a second, in the inversion, strong inversion, we have a VGS minus VT, like this equation, comparing comparing that, this number is a lot bigger, so good GM efficiency is achieved. But the problem is the device size is too large. For example, if you want to drive the transistor in weak inversion, let's say for example in this kind of a bias condition, we are limiting, we are having the fixed current through the device by having this. So, or you can think of just VGS in here. In order to have a same current through the device, mu half mu n cox W over L V overdrive square. In this case, if the current is fixed, to play with the W and V overdrive, if you have a larger W, V overdrive voltage will be smaller and smaller to have the fixed current I0. So overdrive voltage going down and down as you increase the W and W. At some point, it's going into overdrive voltage going too small, so it getting into the weak inversion and subthreshold, eventually subthreshold region, right? So we will see the GM comparison at the boundary of the strong inversion and the weak inversion. We know the GM equation at the weak inversion is ID over C VT, and strong inversion is 2ID over VGS minus VTH. So we will equate that those two are equal at the boundary. So trying to see how much overdrive voltage is roughly represent the boundary of the weak inversion. So here for the same current, take it out, we get the relationship like this. So C is around 0.5, then the overdrive voltage becomes 70 to 880 millivolt. Around this number or below will be sub-threshold region. So if you want to have a strong inversion, try to make sure around V overdrive greater than 100 millivolt or something. But if you are more like GM, you like the GM efficiency, like a small current, so say the maximize the GM out of the fixed current, then you will design for the sub-threshold or weak inversion, so around 100. The potential issue from the weak inversion is that first, there are two things. First is the speed. Input capacitance, the device size is too large, so current density is so low, and device size is large, so first device is slow. The speed issue, slow. Second, so low current density, so VTH variation, device variation will result in large current variation, large ID variation. To reduce this variation, we have to even larger area of the transistor, larger area, because the VTH is sigma, the statistic of the sigma, the VTH variation of the sigma, standard deviation of the sigma is proportional to 1 over square root W times L. So area scale inversely proportional to the scale of the area, device area. So from this fact, we better to have a larger size so that you can have the desired current level. This slide compare the GM efficiency between BJT and MOSFET. So BJT, we know the GM is IC over VT. In MOSFET, depending on the operation, so weak inversion, we have the GM equal to ID over C VT. So strong inversion, we have a 2ID over V overdrive. There are other equation, another variation. So something that we have the square root 2 mu n cox w over l ID, or the the mu n cox w over l V overdrive. So those other two equation includes the mu n cox and w over l. So this kind of factor that depends on the process. So we don't rely on that process dependent parameter. We want to rely on the design parameter like ID, current, and overdrive voltage. Here we have a strong. So if you plot the difference here, so KT 1 over KT over Q is this level for over this kind of GM. So if you have a the ID even for the GM over ID for the fixed current, you get the for the given current, the GM is given by 1 over KTQ, right? So here VT is KT over Q, right? And for the MOSFET in soft threshold region, we have this number 1 over some factor n from the C, the n equal C. So the little bit lower GM, since that number is greater than 1, so we have a lower GM than BJT, but BJT in the strong inversion even smaller, because the equation is given by 2 over overdrive voltage here. So as you increase the overdrive voltage, you get the more current. So if you normalize the current with the boundary of the strong inversion and weak inversion here, so if you have a high current density, then you're getting into strong inversion. A lower density, then you get the weak inversion here, right? So practical strong inversion MOSFET's GM versus BJT's GM is around 4x difference already. So for the same amount of the current you flow, the MOSFET is 4x lower GM. So, but one thing that also make designers more flexible, so they can design their overdrive voltage so that they can change the current density, and that will result in the difference in overdrive voltage, and we can have the different GM efficiency out of the certain amount of current. There's another effect called velocity saturation. So in the, for example, 5 volt device to, let's say, 1 volt device, something like that. If we have a more advanced device, the physical dimension getting smaller, the distance getting smaller. So E field, epsilon V over D, something like that. So getting distance getting smaller and smaller, the E field getting stronger, supposed to drain. So, but the mobility, the velocity in inversion layer here, electron moves across the channel, right? The velocity of the inversion in inversion it was supposed to be linear as we increase the electrical field between the source and drain. So this the slope becomes mu, mobility, but at critical point of the electrical field, which is around 1.5, approximately 1.5 times 10 to the power of 6 volts per meter, then it saturates. So velocity doesn't increase according to the E field. So which is around the Vsat equal to around 10 to the power of 5 meter per second. So once the velocity is saturated, current doesn't increase as much before. So in strong inversion, it was following like a secure law model, but once the gate voltage is too large and drain large, and the current becomes linearized, right? There's the mobility degradation here, and also strong. So we have a vertical strong E field, kind of impede the charge movement from source to drain. So that overall limits the current. So ID in velocity saturation region equal to WCOX Vset times overdrive voltage. So we can see that VDS is proportional now W times V overdrive voltage here. So this is linearly proportional to IDS is proportional to VO. And the GM of this guy, if you take the derivative, so GM going up and up as we increase the VGS for the same amount, for the same size of the device, like this, you get the higher current and current. But in strong inversion, as you get the increase the VGS, you get the larger GM because larger current. But once it passes a certain point, the GM doesn't increase that much. Yeah. GM, this is the absolute maximum GM that you can achieve out of the MOSFET. In IDS and versus VDS plot, so we know that for small GM and small VGS variation, this is saturation region here. So GM is large. Once you increase the current level too much by having larger VGS, then for the same the GM delta here, delta ID versus delta VGS is smaller, right? So the velocity saturation can be modeled with a simple equation, like since the mobility is degraded, right? So mu can be modeled like mu. So V and the E field electron velocity. So slope was the mu that was saturated for large V overdrive. So we can say that mu equal to mu 0 1 plus theta, some proportional factor that V overdrive. So mu 0 1 plus theta VGS minus VTH. So this equation can be plugged in conventional secure law device model like that's shown in here. Here Kn prime is half mu n COX, half mu n COX, yeah. So mu 0 COX. So take that mu onto that. So we have an additional factor that 1 plus theta V overdrive voltage. This can be approximated for large VGS like this, that is similar to the same as the strong inversion. The velocity saturated current model. The ID becomes proportional to VGS, right? So GM can be also found by taking the derivative with respect to VGS. So ID. So we get the complicated mathematics. So finally, it becomes like this equation. So That suppose is okay. So double that GM is proportional to W over L in velocity saturated modeling, and also that is W times COX reset velocity saturation, velocity saturation, velocity saturated velocity here. So we can equate that the relationship here, but this derivation is not that important, so we'll skip this. So what you have to remember is that mu can be modeled like this. Having this kind of a modeling give us more flexibility, or so some non-ideal, it is easier to drive the non-ideality. For example, so ID equal to, for conventional device modeling, when you think about the non-ideality, for VGS is modulated with a pure tone. Since this one is second order square law device, a square law equation, the distortion out of this will be only first fundamental. We have a F0, so F0 tone plus the second order tone F0 to F0 tone is the observed ideally. So let's say if you apply this signal onto your circuit, and then you measure the spectrum out of that, you are supposed to see the only up to second order and fourth order, like an even order harmonic. But in reality, you will see third order harmonic there, 3F0 as well. The reason why, because this kind of equate, if you consider that the this mobility degraded equation, theta VGS minus VTH WL VGS minus VTH square, then because of the factor in the denominator, they can also that actually explain well why we are getting this odd order harmonics out of our circuit. Okay. This is just some of the example for a certain device. As we receive the VGS, we get the different GM curve like shown here. So from this seems like the around 0.7 is VTH. So VTH seems like around 0.7, right? So the boundary between VTH is slit strong inversion is around VGS minus VTH is around 70 millivolt to 80 millivolt. So in this case, and also if you first want to design, we would design for like a overdrive voltage around 0.2, so that it can be like well inside the strong inversion. But if you have a too large overdrive voltage like in that region, then GM doesn't go up as much. You put more current, so in that region the current efficiency GM over I collapses. So we want to avoid this region. Want to avoid velocity saturated region. So try to work with like this region. The weak inversion or the strong inversion is popularly used in many design. So for weak inversion, as I mentioned, you have to make sure the device mismatch is become critical. So device mismatch simulation must be run, so that your design is not does not show any problem. So to run the device mismatch simulation, you have to run the Monte Carlo simulation. in your simulation tool. They will provide some statistic information and give us some variance on the VTH or whatever, right? So remember again, the sigma variance standard deviation of VTH is proportional to 1 over square root W times L. This is something that you have to remember for your design.